The second system that we will study today, which exhibits the simple harmonic motion, is the simple pendulum. Have you seen the pendulum clocks anywhere in your life? Or have you seen anyone hypnotizing the patients? They use the pendulum. How is the pendulum? This is a bob and it is attached with a thread. The other end of the thread is attached with the support. The main characteristic of the thread is it is inextensible. It means a thread which cannot be extended when we attach the bob with it. So, what is a simple pendulum? You have understood well. Let's move on to the situation that how it will be showing the vibrations. On this bob, there are two forces acting. One is the tension in the thread or the string, which is acting in the upward direction along the string. The other force which is right now acting on this bob is its weight, which is acting exactly vertically downward. Here if you observe this bob, is it moving or will it move? No, neither it is moving downward nor it is moving upward. It means tension and weight both are equal and opposite, and no net force is acting on the bob right now, and it is at rest. This point O at which the bob is at rest is also known as the mean position. Now I will take the bob from the mean position O and I will hold it over here for a while and then I will release. This will be the extreme position A and this will be the mean position O. Now at this point A, have you seen what happened with the forces? The tension is now along the string, weight is still vertically downward. Now they are not along the same line, they will not cancel the effect of each other. When they will not cancel the effect of each other, it means that some net force will be available. That net force is responsible for the simple harmonic motion of simple pendulum. The angle between the initial situation or position of the pendulum and the recent situation of the pendulum is theta. This weight, or I will resolve this weight into two rectangular components. One component will be along the string. Now I have made the component which is along the string. How you will check that this is along the string? If you put the scale, they will be aligned. Now the angle between the weight W and this component of weight which is along the string is theta. As you can see that this is the same line and this is perpendicular or vertical line, so this is also vertical line. So this will make again the angle theta with the vertical. Now let us draw the second component which is perpendicular to the string. Now I have drawn this second component of weight which is perpendicular to the string. How you can check? This is the line along which the string is coming and this angle is 90 and this weight is, this component is perpendicular to the that string which we are using. Now SW is equal to mg. So as you can see that this is the side which contains the angle and the 90 degree. So this will be the base of this right angle triangle, and according to the resolution of forces, the base is mg cos of theta. If you check this pendulum, whenever you will displace, it will never move upward nor it will move downward. It means that now tension is balanced by this component of weight, that is mg cos of theta. So there is, as no motion is along this line, so they are equal and opposite to each other. But if you look at the component which is perpendicular to the string, now this will be mg sin theta. One component which is along the string is mg cos theta, as it is the base of the right angle triangle. This one will be opposite to the theta or angle, so this will be mg sin of theta. Now this fourth or this component of weight is having no balancing component, so this is the restoring force which will be making the pendulum to move back to the mean position. So the restoring force in this case is a component of weight, that is mg sin of theta. Let us discuss the complete vibration of the simple pendulum. It is just like a swing. I will displace the bob with my hand and I will release it at this position. The position at which I am releasing is known as the extreme position or extreme point, that is A. After that, when the bob will release, it will start moving towards the mean position. Then after the mean position, it will be having some speed, it will move on to the B, then it will come back to O, then from O it will again move to point A. Again, at the extreme positions A and B, the restoring force will be maximum, as the body is having the maximum displacement from the mean position, and the speed of the body is 0, as it will stop for a while and then it will start moving back. Next is when the body will be moving, it will pass through the mean position. When the body will pass through the mean position, the force acting on the body will become 0, as the restoring force depends upon displacement from the mean position. Here displacement is 0, so the restoring force will be 0, but this body will attain the maximum speed. So we have discussed the mean and the extreme position separately. Now let us see how the body moves in between, from extreme to mean or mean to extreme. As the body will be moving from extreme to the mean position, like A to O or B to O, what will be happening? The displacement from the mean position will be reducing. Because of that reduction, the restoring force will also be decreasing. On the other hand, as you know that velocity depends upon acceleration produced. So here in simple harmonic motion, do remember always the acceleration is from extreme to the mean positions. Now the motion is also along the direction of acceleration, so the velocity will increase. Again here same will happen when it will move from B to A, the speed or the velocity of the bob will increase. On the other hand, when the body is moving away from the mean position and towards the extreme position, like it is going here, or it is going in this situation, what will happen? Acceleration is acting in this direction, motion is in the opposite direction, so the speed of the body will reduce. But when it is moving away from the mean position, displacement is increasing, so is the restoring force. In this situation as well as in this situation, both the situations are same. The body is moving from mean to extreme positions. T is equal to 2 pi under the root L by G. Kindly do remember this formula with full attention, as this formula will be used in numericals and it is very important. Now you can see that 2 pi is the constant, so time period is directly proportional to the square root of length. It means more the length, more the time period. Lesser the length, lesser the time period. More length means long pendulums have long time periods. They move slow. Short pendulums have less time period. It means they move fast. The second thing that is to be considered is G is inversely proportional to the gravity square root. More the gravity, lesser the time period. Less the gravity, more the time period. That is, if the force of gravitation or gravity is less, time period will be more, or the pendulum will move slowly. Or if the gravity is more, time period will be less. That is, when there is more gravity, the pendulums will move fast. So if you have same pendulum of same length, you take its time period on the surface of Earth, where gravity is 10 meter per second square, it will be having a certain time period. But if you take it to the moon, where gravity is only 1.6 and it is reduced, so the same pendulum will slow down. It will take more time to complete the vibration.